we're going to finish off our modern physics unit talking about atomic physics, and we're going to learn some very strange things about the way electrons act inside of atoms. So the first person we're going to talk about is Rutherford, and you should all be familiar with his experiment from chemistry. He shot alpha particles at gold foil. He found that the vast majority, greater than 99.99%, went straight through without hitting anything. And a tiny minority, less than 0.01%, bounced back. And his conclusions, based on that, was that the atom is mostly empty space. With a tiny dense nucleus. And with the electrons orbiting. And this is sometimes called the planetary model because the electrons orbit the nucleus like the planets orbit the sun. Now, so this explains the fact that the atom is mostly empty space, most of them went straight through, so it seemed like a pretty good model. But they started noticing something strange. Okay, when they look at spectrums, okay, if I take white light and shine it at a prism, okay, when it gets to the prism, because there's a different index of refraction for each color is going to refract at different angles, and it spreads the colors out into a continuous spectrum showing all of the colors. And if you remember, that's called dispersion. But if you look at a hot gas, it turns out that the light coming from that is not white light. It doesn't have all the colors. When we put it through a prism, we get what's called an emission spectrum. Because it's hot, it's emitting energy. And you only get a few very distinct colors. Okay? And the same thing will happen, or something similar will happen, if I take white light, shine it through a cool gas. That cool gas is going to absorb some of that energy. And then if we take the energy and put it through a prism, we'll find that we get the continuous spectrum from the white light with a few colors taken out. The colors that are taken out are the same as the colors it emits. So this gas can emit only certain colors and absorb only certain colors. So we're going to make note of that here under Bohr. Okay? Elements. Have their own unique spectrums. And they only absorb or emit specific colors, not every color of the rainbow. And we had to figure out why. Well, Bohr kind of figured out that when electrons drop toward the nucleus, that's a lower energy state. So they're losing some energy. Where does that energy go? Because by conservation of energy, we can't lose energy. So what they do is they emit energy. in the form of electromagnetic radiation. It's often light, but it doesn't have to be light. It could be ultraviolet, it could be infrared. And when they jump up, when electrons jump up in energy levels, it is because they have absorbed energy. So when they're absorbing or emitting energy in the form of light, that's going to correspond to a particular color. So if they make a big jump, a big change in energy, they're absorbing a lot of energy, and that has to be high frequency, so maybe bluer or more purple light. If they're making a small jump, it's only a little bit of energy, so it's either going to absorb or emit, say, reddish light, which is lower energy. But why are only certain colors allowed and not every color? Okay? It seems like the electrons can only make specific jumps. So let's make a note of that. These specific colors allowed corresponds to specific energies. Allowed. And that led Bohr to come up with his model of the atom. So we're going to draw that over here. The Bohr model is going to look like this. You have a nucleus down in the center. And then you're going to have energy levels. We're going to have an n equals 1 energy level or orbit. And we'll have n equals 2, and n equals 3, and so on. Okay? So it looks like the planetary model. We still have electrons orbiting, but the change is that only specific energy levels n equals 1, 2, and so on are allowed. The electron can't be in between. And this leads to something very strange. Okay? Let's imagine I'm trying to walk toward the door from the middle of the room. So I have to get from the door to the middle of the room, but if I'm like an electron, I can't be anywhere in between. So the only way I could get there would be to stop existing in the middle of the room and start existing at the door. I would actually be, it would look like I was teleporting from one to the other because I can't be at any of the points in between. So it turns out that's the way electrons move. And the term for that is a quantum leap. Okay? So when an electron goes from n equals 3 down to n equals 1, it starts out in the n equals 1, it disappears from that state and appears, it disappears from the n equals 3, and then appears in the n equals 1 without being anywhere in between. Now, there's some numbers I'm going to give you. You don't have to memorize these. You can look up in the notes, or they would be given in any problem. For n equals 1, we call that the ground state. The energy of that is negative 13.6 eVs. I'll explain why they're negative in a minute. The next state up, n equals 2, the energy for that one is negative 3.4 EVs. Then n equals 3. The energy for that one is negative 1.51 EVs. And for n equals 4 is negative, the energy is negative 0.85 EVs. And then they continue going up. They get closer and closer together. You'll notice from n equals 1 to n equals 2, there's a gap of about 10, right, from 13 to 3. But then from 2 to 3, the gap is much smaller, 3 to 4 smaller yet, and they get closer and closer and closer together. Our last one would be n equals infinity. Okay? The energy of that is 0. It's not bound at all. And so this is a free electron. So what's that saying? The reason these are negative, if I'm in the ground state, I'm at negative 13.6. In order to get free, okay, I have to go up to 0, so I have to gain 13.6 energy to be free. So another term for that is the binding energy or the ionization energy. Because in order to free it, you have to gain that amount of energy. Now we have a sample problem down here. All right, we have an electron going from the n equals 4 to the n equals 1 energy level. How much energy is emitted? First off, how do we know it's emitted? Well, it has to be emitted because I'm going from 4 to 1, higher energy to lower energy, you're going to emit it. And the way to find out how much is just find the energies of each of those levels. So n equals 4, we said above, is 0.85 EVs, negative. And then n equals 1 is negative 13.6 EVs. So it starts with negative 0.85, ends up with negative 13.6. How would I figure out how much energy is emitted? Well, I would just subtract them. So step 1, the energy emitted. I'm going to put a little symbol here. I'm going to put a little photon symbol because it's emitted in the form of light. Okay? Equals, and I'm just going to do 13.6 minus 0.85. I know there's negative signs on those, but it's kind of an absolute value thing. I just want to know how much energy, so I can just subtract those two numbers. And when I do that, I end up with a value of 12.75 EVs. Okay. Step 2. All right. What is the wavelength of the light emitted? Well, we just found energy, and we need wavelength. The equation that connects those is E equals hc over lambda. Okay? So I can rearrange this, and I would get lambda equals hc over E. Now, h has two values. We have the joule value and the EV value. Since our energy is in EVs, we're going to use the EV one. So 4.14 times 10 to the minus 15th times, c is the speed of light, 3 times 10 to the 8th, divided by, the energy we just found was 12.75. When we do that, we end up with a wavelength of 9.74 times 10 to the minus 8th meters. Now, it turns out that that wavelength is smaller than light. Light has a wavelength usually somewhere around 6 times 10 to the minus 7th. This is minus 8, so it's smaller. It turns out that this is ultraviolet, okay, because shorter wavelength is higher frequency. Violet's the highest frequency of light, so this is beyond that, so it's ultraviolet. And it turns out this might be something that'd be good to know. Anytime I drop down to the n equals 1 energy level, it turns out we're not going to be able to see it. It's going to be ultraviolet light. When you're dropping from some higher level down to n equals 2, that's when you get visible light. In any of the other transitions going down to 3 or 4, then you have less energy and ends up being infrared. Could an energy of 9 times 10 to the minus 19th joules be emitted? This is about as hard as these problems can get, especially because I've mixed up my units. So first off, I have to convert this 9 times 10 to the minus 19th joules into EVs because my energy levels are all in EVs. So the conversion is, I'll write it over here on the side, 1.6 times 10 to the minus 19th joules equals 1 EV. All right, so I have joules. I'm going to have to divide by the joules to make it cancel to get EVs. So my energy is going to be 9 times 10 to the minus 19th. Okay, joules divided by 1.6 times 10 to the minus 19th joules per EV. And that's going to give me a value of 5.625 EVs. Okay? Now, it says it's in the n equals 3 energy level. So n equals 3, the energy for that was negative 1.51. All right? Now I'm going to change by 5.625, and I'm going down, right? So I can find the energy that it's trying to get to by doing negative 1.51 minus 5.625. And when I do that, I find the energy it's trying to get to is at negative 7.135. So can it end up at that energy? And it turns out, if I look back up here, all right, okay, n equals 2 is at negative 3.4, n equals 1 is at negative 13.6. It's trying to end up somewhere in between these, and it can't, right? That's what Bohr figured out, is it can have an energy that's not at one of these energy levels. So the answer is no, because that doesn't match an energy level. So we're going to say, no, it can't do it, because it's not at an energy level. Okay, and what that would correspond to is that particular color could never be emitted because it can't jump down to that energy level. So that's why only certain colors are in the spectrums, because only certain transitions are allowed. Okay, top of the next page. So we're going to kind of sum this all up and talk about what quantum mechanics is. Okay, so all of this strange stuff, light being a particle, okay, electrons being able to teleport from one spot to another, are the beginnings of quantum mechanics. And a quantum is a tiny step or piece. So so the tiny steps in energy, it doesn't continuously go upward in energy. You can be at n equals 1, you can jump up to n equals 2, okay, you can take that step or that leap, but you can't go, you can't be any place in between. Same thing, light seems to come in little pieces or little chunks called photons. So our examples that we're going to talk about with that is light comes in pieces called photons, and energy levels come in specific steps. Now, it turns out there's another thing we've talked about that comes in quantum, and it's charge. Okay, the person who discovered the charge on an electron was Millikan, and I may have mentioned this experiment before. But what he did was he put an oil drop, which he knew had a negative charge. So I'll make a little mark there. It's a negative charge between two metal plates, and gravity was trying to pull down on it. But then he charged the bottom plate so it was negative and the top plate so it was positive, so then there's an electric force pushing up on that negative because it's being repelled from the negative plate. And he could calculate the force of gravity, and he knew the electric field, and if he got it to just balance, he knew those two forces were equal. So he turned up the voltage until those two balance, and the oil drop remained suspended. He found the charge on the oil drop, and he found it could always be 1 times the charge on an electron, 2 times the charge on an electron, 3 times the charge on the electron. It was always a whole number of this same charge, and he decided that must be the charge on the electron. Okay, so he found the charge on the electron. And then last thing we're going to say about it is a charge comes in steps or quanta as well. Just like energy levels can only be n equals 1, n equals 2, n equals 3, just like you can only have one proton or two protons or one photon or two photons or three photons. You can also have charge only equal to 1 times E or 2 times E or 3 times E. So charge also comes in steps.